So, good afternoon, everyone. Hello. I hope you have listened yesterday's lecture and you must have also got mail from HBNI today. So, during my lecture, I will be asking a few questions and I want that answer to be given either at that time or you can mail it. So, it will be mailed by 7 p.m. of the same day. So, the questions will be very trivial.
Hello,
And
ma'am. Hello.
Hello.
हाँ,
Yes.
mail to same email ID ना?
Yeah, you can mail it to same email ID or you can mail it to my email ID also. It is there in that lecture you can see.
Okay.
Or you can write it down.
Okay, ma'am.
It
Okay.
is SHASH. When I will be showing my slide, you can see my email ID also. Okay,
Okay.
so you can send it anywhere. But it is
Okay.
to be more interactive because no, if I know whether you are able to understand or you have got any queries or so I can modify or this lectures can be more fruitful. So that is the point behind the questions.
Okay,
But
ma'am.
it is mandatory for everyone to answer those questions. Okay. So can any one of you tell me what was my yesterday's question? Anyone? So, okay, can I ask some of you to put on your camera, those who can? Like, I think WebEx people can put on, who is attending on the WebEx can put on their camera. So, just for maybe starting 5 minutes. Okay. Hello. So, you are, maybe you can, Priya. Priya is there, right? Priya?
She's
Okay.
muted.
You are muted, Priya.
Okay. Myself, Priya Bhagat.
Okay. From which place? Which university?
Mumbai, Murbad, Shule College, which is affiliated to Mumbai University.
Okay. Okay. Hello. So, did you listen to my yesterday's lecture?
Not completely, half only.
Okay. 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 So, today also I will be posing some questions
Yes, yes.
and for
Okay.
which you have to answer.
Yes, yes.
And this is from
Good afternoon.
Echika Kalpakam. Okay.
Good afternoon,
So,
my
I
name
know
is.
Shivam,
Yes,
right?
ma'am. Yes, ma'am. Yes, ma'am.
Okay. So, did you listen to yesterday's question?
Actually, yesterday I came late to the class, but that question, whichever you asked, ma'am, what is the uses of in forward bias and reverse bias?
Yes. Yes.
So,
Yes.
forward bias we can use in amplifications. In the amplifiers, we can use reverse bias, and we can use in the switching also, detectors also. So,
Okay, reverse bias you are using for detectors. Radiation
and
detectors we use in reverse bias. Okay.
yes, and switching also means forward and combination of forward and reverse.
Yeah, it
We
can
can
be
use.
used as a Zener diode. Basically, I think you are talking about the Zener diode where reverse bias it can be used as a switch. Okay, good. And other people, anyone who wants to put on their camera? Okay, so yeah.
Madhur Patel said.
Madhuri. Yeah, Madhuri.
Yes, ma'am.
Madhuri, from where you are?
I'm from the Mumbai University BNM College, Bhiwandi.
Okay, so could you listen to my talk yesterday?
Yes, ma'am. I've written given the answer also. What question did you did given to us that in which application forward and reverse diode is used? I've written in the chat section itself.
Okay, okay. Okay, so today we will be starting on share. Okay, so as yesterday at the starting, I said that first I have started with the semiconductor part, just a brief introduction on semiconductors. And okay, before going to the second part, which is going to be the single crystal growth. So anyone has any question, any doubt on the semiconductor, basics of semiconductor? So we will just let me know now, then I will start this. Anyone?
Ma'am, I have one question.
Yeah, sure.
Ma'am, that is, I mean, a bit experimental. Can I ask?
Yeah, sure. Please ask.
Ma'am, I mean, if I'm, for example, silicon is a semiconductor
Hmm.
So if I am making any silicon-based solar cell, and if I am trying to do any doping of, any other material on silicon, like how to do the accurate doping in practically, in lab. So I am getting like good literature. If I'm comparing, I will get a good, result.
So
Of-
Jyoti, it also depends on like which method you are using for doping. So can you tell me which method you are using? Because
Ma'am,
I
salt
think
gel.
that you are asking this question from your own
Yes,
experience.
Ma'am, salt gel method, but after time, my substrate was FTO, so but I'm not getting such good results like if I'm doping. So what is the error I'm not able to find? Like I am doing salt gel methods. So
Okay, Jyoti, what we can do, because your query is very specific. So you can see my email ID na, on the screen now, shash,
yes,
shash@.
ma'am, yes, ma'am.
So let us discuss your problem there rather
Okay,
than
okay, ma'am.
spending
Sure,
some
sure.
hours.
Yes, okay. Sorry,
And
ma'am.
we will
Sorry.
try to find out what is the best
Yes,
solution for your
yes,
specific case.
yes,
Okay?
ma'am. Thank you so much.
Welcome. So now today, in the section, now yesterday we were talking about the semiconductors, right? So as you all know, the most important semiconductor is silicon. Then we have got germanium. And yesterday we were also talking about the compound semiconductors like gallium arsenide and all those things. And we also saw that to have a proper band structure, this material should have a crystalline. And I think in the first few lectures, Dr. Vinita Gupta has already covered the crystal structure, how it is important, different kind of crystal structures and all those things. But then when we come to actual device applications, so we have to know how these crystals are made. So my today's lecture will be single crystal growth. So techniques will be there. So I will be starting briefly on the theory of single crystal growth and then covering different crystal growth techniques. And in this, I will be also covering like growth of silicon and germanium and gallium arsenide. Okay, so what is basically single crystal? Single crystal, you all know that it is a periodic arrangement of atoms or molecules in the 3D. Now, what is single crystal growth? So it is controlled phase transformation from a disordered fluid phase into a highly ordered solid phase. So highly ordered solid phase you can all understand, and disordered fluid phase means that initially it can be amorphous, it can be polycrystalline, or it can be in the solution or something. And from this disordered phase, we are transforming into a highly ordered solid phase. So that is the very fundamental definition of single crystal growth. Now, whether considering nucleation or growth, the transformation from solution to solid is the same. Namely, now, what does this mean? No? How does single crystal growth starts? So initially there is a nucleation and there is growth. Nucleation is nothing but the first seed crystal. So if I say that I have to grow a very big single crystal, say this. Okay, but this is my desired single crystal. But we have to start from here. Okay, there will be a very small initial growth or anywhere from there. It can be in the middle or something. So this is called the nucleation. And first is nucleation. And then this nucleus, or in our crystal growth, it is called the seed. It then starts growing. It will grow in all the directions. So growth. So basically single crystal growth is comprising of two parts, that is the nucleation and the growth part. And excuse me. Okay. So the reason for this transformation from solution or solid. So solution means if we are growing it from a salt solution, or we are growing the crystal from polycrystalline material, the reason for this transformation from the disordered phase to a ordered phase is namely is one and only one, and that is that free energy of the initial solution phase is greater than the sum of free energies of the crystalline phase and the final. So everything, remember that free energy of the full system has to decrease, then only we are able to transform. So free energy of the initial solution phase is greater than the sum of the free energies of the crystalline phase. So that is the driving factor for the single crystal growth. And addition of new atom, ion or polymer to the characteristic arrangement. So because of the decrease in the free energy, the new atoms or ions or whatever is there, whatever the material is made up of, it gets added. And this added under a physical condition which is close to the thermodynamic equilibrium. So thermodynamic equilibrium is a phase like we are say growing. The most popular growth technique is, you all know, is like solution. We put the salt solution we all make, and we have say beaker is there, and we put water. This is all water. And in this we put say NaCl. And then we have this dissolved NaCl in this, and then slowly one crystal forms, and then it becomes bigger and bigger. Or you can have multiple crystals like this. So at thermodynamic equilibrium, what happens? The number of NaCl in the solution and in the solid phase are equal, and they will be changing from one phase to another. So like NaCl solution and NaCl solid, they are in equilibrium. So the number will not change. So we cannot grow a single crystal under equilibrium condition. So condition has to be close to the thermodynamic equilibrium, but not at thermodynamic equilibrium. We will be understanding this point in the coming slides. Now, before going into actual techniques and all, so single crystal methods are basically melt, solution, vapor growth and hydrothermal. Melt means we are melting the material. So we will be taking it to high temperature. Any material, it can be like silicon. So we can say silicon is there. So silicon is melted. Silicon melts at around 1400 degrees centigrade around. So we take the silicon polycrystalline material to 1400 degrees centigrade and then we grow it. So in the melt growth technique, we have the Bridgman technique, we have the Zekrolsky technique, Bernoulli technique and floating zone technique. So I will be covering all these four techniques today. Now coming to the solution growth. So solution growth is like I was just mentioning earlier, we have got this salt or NaCl is like one example. Or sugar crystal. So this we can grow from solution. So we have a solute, we have a solvent, and we dissolve the solute in the solvent, and then we can do different way. So growth from solution is like slow cooling technique, or it can be evaporation technique. Then we have got vapor growth. So vapor growth is more, we are evaporating. Now in the melt, we were just melting it. In the vapor growth, we are evaporating the material, and then we are making the, then the vapor is condensed and it forms a single crystal. But this is more utilized for thin films. Because it will be very slow and it is more useful in the thin film deposition. So when we are, and you may think that thin film and single crystals are different, not so different. Like we have got thin film, single crystal, thin films also. So for the deposition of single crystal thin films, vapor growth is used, and this I will be discussing in my next lectures, which will be on the thin film part. And then hydrothermal growth. So, okay, for the vapor growth, we have got direct vapor or reactive vapor. So, reactive vapor means you are using two different vapors, and then they get react and form a new material, or you have a big compound, organic compound is there, which breaks and then make a new compound on of which the crystal is growing or the film is growing. So, we can have both the techniques. Now coming to the hydrothermal growth, it is generally used for the growth of SiO2, and I will be discussing it. Now stages of single crystal growth. So as I have told you that, okay, one thing is like I would request all of you to join bit early because already 15 minutes are over. So no, when I will be taking attendance, so I will sure that within 10 minutes all of them are there, and we will be taking the attendance at maybe around 2:40. So anyone joining after 2:45, please see to it that. Okay, now stages of single crystal growth is the first stage, as I said, is the nucleation. So nucleation is one of the two major mechanisms, and it is a first order phase transition. The process of generating a new phase from an old phase whose free energy has become higher than the emerging new phase. So the free energy of the, so let us assume that we are growing from solution. So we have a solution. This is the initial phase. And we have a solid, which is a crystal. So this is the crystal. So this is the final phase. And so first there has to be nucleation, and this transition is a first order transition, phase transition. And from this, so the free energy of this is higher than the free energy of this. So free energy of this phase is greater than the free energy of this phase. So you can see, so the total energy of the system. So from liquid to solid, there is a decrease in the free energy. So this is the liquid phase, this is the solid phase. So there is so this delta G is negative. So that is the first condition, that the Gibbs free energy has to decrease for a single crystal growth. Okay. So no question, right?
Ma'am, I have a question.
Yeah, please.
Yeah, in the phase transition part of the first module, we had learned that in the first order phase transition, the G remains continuous, whereas entropy and volume have a discontinuous change.
Can you come again?
In the first order phase transition,
Yes.
Gibbs free energy doesn't change discontinuously. It has
Yeah, it is not
it's
continuous,
the
right?
same.
Yeah, so we will see that it is not very continuous.
So if it's the same, then how are we observing a
is a-
decrease in
As
phase
you know
energy?
that generally, if I take a condition of this water to ice to water, water to ice, so there is a latent heat. So that is a second order in that case, but in the energy diagram. Is that what you are asking?
No. What I'm asking is, there is a decrease in Gibbs free energy in the nucleation, but it's also one of the two major mechanisms of the first order phase transition. So, but first order phase transition means that there is no change in Gibbs free energy, while there is a discontinuous change in entropy and volume. So, how are these two facts not contradictory?
Volume is changing in this case because you are going from a dissolved phase to a solid phase. So there
Yeah,
is
but
a
the
change.
Gibbs free energy is also changing.
Yeah, Gibbs free energy is changing when there is a growth of single crystal, and it is a first order phase transition because there is no discontinuities there.
Okay, so a smooth transition is possible.
Yes.
Okay.
So nucleation occurs via the formation of a small embryo of the new phase inside the large volume of the old phase. And another prominent feature of nucleation is metastability of the old phase. That is, the transformation requires passage over a free energy barrier. Okay. So what happens exactly is the process of nucleation is we have got, like in this case, I am showing you, let us assume that this is inside a container. And we have got for many atoms or molecules are dispersed in it. Now initially there will be some atoms are coming together and forming the critical particle. So nucleation rate is the total number of cluster of atoms per unit volume and number of clusters of critical size per unit volume. Okay. So we have got number of clusters of critical size per unit volume is defined by the temperature, and we have the total number of clusters of atom per unit volume. So nucleation rate is how it is changing with respect to the delta F is the change in the free energy. So if we see this homogeneous nucleation, so we have, as we see earlier, there is a spherical ball of solid of radius in the middle of the liquid, and we have the delta G is of solid and this is the liquid phase. So this is negative. Okay. So this is negative. So this is the homogeneous nucleation. So what happens basically, we see that the free energy per molecule of the new phase is less than the solvated phase, only applies to the bulk of the new phase. So though we are seeing that the new phase, the energy is less, but this is only for the bulk of the new phase. The surface molecules are less well bound to their neighbors than are those in the bulk, and their contribution to the free energy of the new phase is greater. So what does it means? So we have this, okay, and our, see, this is my nucleation, okay, very small. And though we are saying that this is in the solid phase and there are molecules in the liquid phase also. So the energy of the molecules in the which are in the dispersed phase is obviously high. But if we look into this small thing, okay, should I make it bigger? Okay, I think you are able to, you can see it. So the one atom molecule which is there in the middle, and we have got different on the side. So the energy of this middle one here, this energy is less, see E middle, and energy of this one which is on the surface. So this is having much higher energy than the middle one. So this middle one is the bulk energy which we are talking about. So we see that the free energy of the new phase is less than the only applies to the bulk of the new phase, means for this atom only the logic applies that the energy is less, whereas the atoms which are on the surface, this is not so. They have got much higher energy, and that's why they can come out. So at any given time when a nucleation is there, so if I see we have a system like this and we have a growing nucleation is there, and then again, can you all see this? Is
Yes,
it
ma'am.
visible?
Yes, ma'am.
Okay. So the atoms or molecules which are on the surface, they can leave this. Some can leave and some can join. So this can always keep on happening. Some are leaving and some is joining. So this is the equilibrium process, and under equilibrium, the number of joining and number of coming out will be equal. So there will be no growth. So we will be making the circumstances, the environment, so as the number of joining is more than the number leaving. And because they are leaving, why they are leaving? Because be the difference, the free energy of the molecules on the surface are larger. So they have got more energy, they can leave the bulk. Okay. So let us see the difference between the free energy per molecule of the bulk and that of the surface is referred to as the interfacial free energy. Okay. So this difference we were showing is the interfacial free energy. And this concept will also come in the thin films, we will see. So the interfacial free energy is always a positive term and it acts to destabilize the nucleus because the nucleus is this. Okay. So the energy which this atom is having, this atom is having, this atom is having, it is trying to destabilize the nucleus which we were trying to form. And as a consequence, a very small size when many of the molecules reside at the surface, the nucleus is unstable. So initially, this nucleus is unstable and the number of, they are leaving, there will be many atoms which will be leaving the nucleus and some will be joining also. But this does not go on forever. So we come to adding even one more molecule just increase the free energy of the system. So such a nucleus will dissolve rather than grow. But once the nucleus get large enough, the drop in free energy associated with formation of the bulk phase becomes sufficiently high, then the surface free energy is unimportant. And every addition of a molecule to the lattice lowers the free energy of the system. So now what happens is there, like we have reached, so now when it is very large, so number of the atoms which is inside are more than the numbers of the atoms which is sitting on the surface. So the total bulk energy is now decreasing. So though this interfacial energy is trying to disrupt the growth of the crystal, but because the bulk, there are a number of more molecules inside the bulk, so the total energy of the system keeps on decreasing. So here if we see that delta F is the change in the free energy of the system due to the formation of ball of radius r. So we have got two components. So here you can say this is F, free energy, and this is r. This is the size of our nucleus. So this is the r. Here you can see. Now we have got, this is the surface
Excuse
term.
me, ma'am. Ma'am, sorry to disturb you.
Yeah, please.
Ma'am, I was saying is that when will the assignment be given?
It will be any time.
Okay, okay. That's all. Okay, thank you, ma'am.
Between any time I will give the assignment. Okay.
Okay, ma'am. Thank you.
So that is the main, like the idea behind that. At some point I will give, it will not be an assignment, it will be just one or two questions which you have to answer depending on how you have listened to the lectures and all. So it is not really in that way, but it will be counted in your overall understanding and during your, because the assignment is before the Viva, there will be one assignment also that will be, so some marks will be taken care there also. Okay.
Ma'am, since this topic has already just been brought up as
I'm
well,
not
I would
able
like
to
to also
hear you
ask one thing.
properly. Excuse me. Your voice
Okay,
is not
okay.
coming properly.
I'm saying since this topic has been brought just now, I would also ask one thing. We received a mail today or yesterday that because of less interactions in the classes, there would be some questions that would be posted that we'd have to answer by 7 p.m.
Yes.
So yeah, so those questions would be asked just in the class or they would be mentioned in the chat as well, because it's not tough to keep score of all the questions that would be asked and not know which question is to be answered by 7 and which is just for us to ponder upon.
I will be asking it during the class and at the end also I will be repeating them. Okay. So
Okay,
that
that
there
would
is
be
no
good.
ambiguity. What do you have to answer? That
Yeah,
is
that's what I was curious
yeah,
about.
because and if by the end of the class you are still in a confusion which question to answer, you can ask me.
And where would we give the answer to these questions?
You can answer either to that mail which has come to you, or you can use my email ID. It was there, or I can write it down here. Sorry, just wait.
Ma'am, you can maybe just type it out in the chat box so that we can copy it.
Okay, sure. Can you help me with the chat box? You'll have to stop. So this is my email ID. So it would be nice if you can all answer here. And yesterday, I asked just one question. It was there. What are the devices in which you use a PN diode in forward bias and in reverse bias? So it was a very simple question. So those who have attended may be knowing it. So today also, whatever I will be asking, it will be very basic. So it is not like you have to have a very prior knowledge or something. Whatever we will be doing today, it will be covered in that. Okay. So you all have got my email ID.
Yeah, we can see it in the chat box.
You are not able to see it on the chat box?
Yeah, we are able to see it in the chat box.
Yeah. Okay. Okay. So then should I go forward with the class?
Yeah, sure, ma'am. Thank you.
Okay. Okay. So this is the free energy of the full system. What we are seeing here. It has got two terms. One is the surface energy terms. This is the surface energy term. So surface energy term is R square dependent. And this is the bulk energy. So surface energy is coming from the all the atoms or molecules which is sitting on the surface. And the bulk is inside. So bulk is dependent on R cube dependencies there. And bulk energy is negative because it is trying to stabilize your nucleus. Whereas surface energy is positive because it is trying to disrupt the crystal which is growing. So as the R of the nucleus, that nucleus which was growing here which is growing. So as R increases, we see that at a given value, first initially it will start, this is the total value, delta F. So this is the delta F. So initially it is increasing because this R square term is dominating at low values of R, very small R. But later on the bulk energy will take over. So once this R star is called the critical radius. Okay. So once the nucleus which is growing, it will cross the critical radii, it becomes more stabilized and it starts growing. Before it reaches the critical radii part, the growth is less and it has got more tendency to disintegrate. So this is the importance of interfacial free energy. Now coming to the critical radii. So there is an intermediate size at which the free energy of the system is decreased where the nucleus grows or dissolves, and this is known as the critical size. This phenomena is known as the Gibbs-Thomson effect. The existence of a critical size has got a number of implications. First and foremost, because nucleation of the new phase is the result of fluctuations that bring together sufficient number of molecules to exceed the critical size, the probability of nucleation will be strongly affected by the value of the critical size. Okay. The nucleation can be controlled to some extent by modulating the critical size, which in turns is a function of the interfacient energy. Smaller the interfacient energy, the smaller the critical size, and more likely nucleation becomes for any given supersaturation. And as a consequence, by varying either the solution composition, here we are taking that we are studying, we are growing the crystal from solution or supersaturation, the probability of nucleation can be manipulated. And this can be achieved by changing the temperature, concentration, composition of the medium or the volume of the medium or presence of a foreign particle. So what exactly does this say? There are 4 or 5 points are there and you may think what is it saying. So first thing is that we have to see for the growth of a single crystal, what is most important is we have to see that the nucleation which has started nucleating, the solid which has started nucleating, it should reach the critical radii. How it should reach the critical radii? And we can do changes. What are the parameters which we can change for that? The parameters are the temperature we can change. If it is a solution growth, we are growing from solution. So we can think of like salt solution is there or a sugar solution is there. So we can go to the supersaturation. So we can put more, we can dissolve more salt in it. So we reach the supersaturation. So there will be more crystallization will be there, or we can decrease the temperature. Okay. So our volume of the medium can be changed. So concentration, composition, volume, temperature, or we can introduce a seed kind of thing or a foreign particle. So this all leads to a nucleation, and the nucleus will be greater than the critical radii so that the single crystal growth takes place. Okay. So here I will take just 1 minute break and then I will again come back. You can just go through whatever I have told till now and then we will continue. Okay. Okay. So we have learned about nucleation. Nucleation is the first part of crystal growth, and what are the different things which are affecting the nucleation, and what is the importance of the critical radii. Now there are 2 types of nucleation. In the earlier you have seen that it can be homogeneous nucleation or heterogeneous nucleation. So here we have seen that homogeneous nucleation. So there are 2 parts in the nucleation. It can be homogeneous or heterogeneous. So what does it mean? Heterogeneous nucleation means that nucleation is happening on a foreign surface. Means it is not same as the material which we are growing. And homogeneous nucleation is we are using the same material to nucleate it. So we are introducing something. So we have got a solution like we have here, we have a solution, and here we are introducing a foreign particle. So as a which is acting as a giving a point where the nucleation can start. So if I am I'm growing NaCl and I am introducing a NaCl crystal here, very small crystal. So this will be because same material, same thing. So it is called homogeneous. Yes, nucleation. But many times we will see that heterogeneous nucleation is favored. So why heterogeneous nucleation is favored? Because the presence, so heterogeneous is a foreign surface. It can be like the walls of this crucible. So here you can see that the nucleation is happening on the wall. So here this heterogeneous nucleation, we have got the crystal is growing on the wall of the crucible or a beaker, whatever you are using for the growth. So the foreign surface can be used to exert greater control over nucleation, and the interfacial energy between a crystal nucleus and a solid substrate is lower than that of the crystal in contact with the solution. Means this interfacial energy, and when it was initially in contact, if the solution is here also. So this interfacial energy, it is less. Why it is so? Because the molecule in the crystal can form bonds with those in the substrate that are stronger than the bond of solvation. So rather than this, they are. So this kind of thing you can think in terms of thin film growth. So in thin film, you have got a silicon substrate, or you have a quartz substrate or strontium titanate, and your material is coming and getting nucleated on the substrate because the bonds which is getting formed on the substrate is stronger. So, or even so, if you have must have seen, like you put your sugar solution is there. So when if it is a sugar solution and you are trying to crystallize it, you will see that the crystallization is happening on the surface of your beaker. If you have a beaker like this, so if you see, there will be, it's happening on the surface. It is not like on the middle there will be one crystal and which is forming. First crystallization, if you are not trying to control it, it will get on the wall, because so that is like a foreign surface, and the molecules in the crystal are forming bonds with those in the substrate, and they are stronger than the bonds of solvation, because the enthalpic contribution to the free energy comes primarily from chemical bonding. So stronger bonds leads to smaller interfacial free energy. So interfacial free energy is smaller, so the bulk energy is more. So more and more nucleation will be there. And the strength of bond at the interfaces strongly depend on the structure and chemistry of the substrate. So if the atomic structure of the substrate surface is closely matching particular plane of the nucleating phase, so that lattice strain is minimized, nucleation occurs preferentially on that crystal plane. So it is like if you are using a single crystal to like epitaxial growth, or we are using silicon substrate for the growth of gallium arsenide or something like that, or when we are growing a single crystal thin film. So we always see that the substrate is matching closely with the, or the some particular planes of the of your substrate is matching with the some planes of the crystal. So strontium titanate is there, then yttria stabilized zirconia is there, then quartz is there, silicon is there. So these single crystals are, that's why used for the growth of crystalline thin films, because some planes have got matches with the crystalline structure, crystal planes of the material which you are growing, and so, and because of the formation of the bonds with the your substrate, they try to nucleate and grow the crystal. So this is basically heterogeneous nucleation. And now what are the factors which affect nucleation and growth? So now there are two competing processes. Now, one is nucleation. So nucleation is like 3-4 molecules are just coming together, forming a very small, maybe it can be greater than, with the radius of greater than the critical radii, or it can be smaller than the critical radii. Okay, so there will be a nucleus. But which nucleus should grow? And thus all the, if we are not controlling, like we are not putting a foreign particle, so is it like all the nucleus will grow? And if all the nucleus it is getting nucleated, it all grows, then it will be a polycrystalline material. That is not what we are wanting. We are wanting a single crystal material, right? So how to control this? So which factors control the size and purity of a single crystal? So if nucleation rates are slow and growth is rapid, large crystal will result. On the other hand, if nucleation is rapid relative to growth, small crystal or even polycrystalline samples will result. So let me draw this again. We are thinking of NaCl. So NaCl is there, then we have got water. Water plus NaCl. Now there is nucleation. So if I leave it like this, so what I do, I make a supersaturated solution of this. Supersaturated solution at a given temperature T, which is greater than say room temperature. So NaCl is there. So we have got, and it starts nucleating. So if I leave it like that, it will be not a single nucleus, there will be multiple nucleus. So I have got say one nucleation here happening. One here happening. And one say here. This. Now they all will be competing with each other at a given time under equilibrium condition. And which one will grow? Now, if we make the circumstances so that the nucleation rate is less, but the growth rate is more. That is what we are saying. The growth is rapid. So like if I increase the temperature or increase the temperature. So if we increase the temperature, it will start dissolving more. So the growth rate goes down. But if I decrease the temperature, I am slowly cooling my temperature and coming to say room temperature. So this growth rate will increase. And if we keep on say steering, we are steering this. So I am like prohibiting the nucleation. So only one is growing and rest all I am not allowing it to nucleate here or nucleate here. So what I am doing? I am trying to make that nucleation rates, and I am decreasing the nucleation rate, and I am trying to increase the growth rate. So I will have a big crystal. But on the other hand, if we can, if the nucleation rates are higher, so there will be many nucleation like this. So there will be one crystal forming here, one crystal forming here, one crystal forming here, one crystal. And they may have they may not be all in the same plane. So there will be some difference in the plane. So it will be ultimately a polycrystalline material. So if nucleation is rapid relative to growth, small crystals or even polycrystalline samples will grow. So we have to have a very good single crystal, big single crystal, we have to increase the growth rate and decrease the nucleation rate. So what can be done to increase the growth rate? So in order to attain rapid growth rate, so we have to grow microscopic. So diffusion coefficient must be large. Diffusion means this is coming and setting here, this is, so what I have to do, that all whatever is there in the solution or in the melt, they should come and join the nucleus which is growing. So like hence crystal growth typically occur via formation of a solid from other phase. So like if it is, we are growing from liquid melt, so we will be decreasing the temperature. Or if it is growing from vapor, so we will be condensation has to be there. And solution, if it is growing, so we have to see that precipitation should be happening, right? we are decreasing the temperature. So, but there is always a problem associated or some difficulties is there. So what is that? If the growth, there will be defects. So what are the defects in single crystal? You know that there will be vacancies are there, or there can be dislocations. So if the growth is very fast, means many crystal atoms are coming and sitting, so there will be, so we have to have a equilibrium of the growth and nucleation. So growth has to be basically slow, but not so that it starts to dissolve. Okay. And how to control the nucleation? So nucleation can be controlled by cooling off melt, like we did the temperature, or we can put a temperature gradient, or we can introduce a seed crystal. So seed crystal is basically homogeneous nucleation. So homogeneous nucleation by introducing a seed means I am growing this NaCl. NaCl is there, and I am introducing a NaCl crystal here like this. So this is the seed of NaCl, and then whatever, and I am also like stirring the liquid so that I am not allowing any nucleation on the wall, and whatever, and the temperature I am setting it so that whatever the molecules are coming, they will start to nucleate on this seed. So this is called the seed crystal. So these are the techniques to control the nucleation, control that there is not multiple nucleation, there is a single nucleation, and it grows into a bigger crystal. Okay. No problem till now, or you want to ask
Hello.
something, ask, and then I will go ahead with the different methods.
Ma'am,
Because I know this is a different, you must have not read about single crystal growth earlier. So we will be going bit slowly, and ask me. So someone was asking something.
yes, ma'am. Ma'am, in case of precipitation formation, when we form the precipitate, then we do the digestion for 30 or 20 minutes. So it's for
What?
crystal.
After precipitation, what you do?
That in practical procedure we did the digestion, that heat that precipitate for 30 or 35 minutes on water bath, heat that precipitate. So it's for crystal growth, na?
Yes, yes, yes. You are
It's-
giving the time for the growth.
yes, that means we are increasing the size of that pure crystal.
Precipitates. But
Yes,
when you are precipitating it, so basically you are, there is many nucleus. Because there
Okay.
is many. Now you are not getting one single crystal. There are many. So that means you are not controlling the nucleation. Because there are many precipitate. But when you are leaving it for in the bar, so those precipitate size increases. So that is single crystal growth.
So heating does that small particle to dissolve and then deposit on larger one. So like that it is.
For that you have to change the environment so that only few precipitates remain and they grow in bigger size. Like you have to do some stirring so that so many precipitates are not there, and the growth, or you can change the temperature of your solution. So you have to
Yes.
see which will lead to the growth and decrease the number of nucleation sites.
Okay.
Any other question?
Yes, ma'am. I have one. Regarding the single crystal growth from solutions,
Hmm.
even when we have homogeneous solution, any kind of mechanical disturbance can lead to multiple nucleation sites.
Yes, exactly.
Yeah, so I can see it happening in heterogeneous because the environment is different in different points of space within the solution. But for homogeneous solution, there should be some kind of a translational symmetry from point to point. So why does any mechanical disturbance lead to multiple nucleations?
If you are having a supersaturated solution, in case of a solution, so you are having a supersaturated. What do you mean by supersaturated? It means the number of a solute in a given solvent, it is the maximum which you have dissolved, right? So it is in a thermodynamic equilibrium part. Now you are entering a foreign body is entering. So it is giving a point where it is giving a point to to decrease the free energy of the system, and the foreign body will act as the point of nucleation. And all the, because this your solution is in the supersaturated, it is already supersaturated. So this foreign body will act as a nucleation, and they will start gathering around it and lead to the formation of a single crystal. So this is similar to like your cloud CD, right? So you put a foreign body and it nucleates, and then cloud seeding happens. Or similarly, if you must have seen that if you have got like on the, you have a very cold water is there, and you put a foreign body and it becomes ice. Otherwise, like at maybe around 1 degree or 0 degree, around 0 degree, there is no formation of ice, but you put a foreign body and the ice formation takes place suddenly. So that is how it is called, that supersaturation is there. So
Yes,
that is why
that's
foreign body is decreasing the energy. The introduction of the foreign body is giving a way to decrease, for the system to decrease its energy. That is called supercooling.
that's why I'm asking that even if we put a single, let's say a single nucleation point, any foreign body that acts as a nucleation point,
Yes.
and
Yes,
mechanical, and there is a mechanical
leading to the decrease in the energy. The system will try to decrease its energy. And when a foreign body so it is like with the foreign body, your whatever molecules is there in the solution, it is able to form some kind of chemical bond. It was not able to make chemical bond with each other because it was in a thermal equilibrium. So whatever bond is getting formed, the similar number of bonds is breaking also in your supersaturated equilibrium condition. Now you are changing the equilibrium condition. So growth always, single crystal growth always happens near the equilibrium, but not at equilibrium. If your system is at equilibrium, there will be no single crystal growth. So your foreign body, whatever you are adding it can be the same particle also. You are adding to it, so it will try to achieve a lower energy status, and that's why that happens. Okay.
in a hypothetical case, if we have a supersaturated solution that was not initially at equilibrium, let's say we are continuously stirring it, then we put the foreign body, so nucleation will not happen in that case either.
If you are stirring it,
If we are
so
continuously stirring,
you are not leaving it to the in equilibrium. No? You are giving a force from outside because you are stirring it.
even if it is
To itself, then only it will try to achieve minimum energy, right? And I think if you have got any more question, you have my email ID. So you please write to me, and then we can continue this discussion. Okay. Now, methods of growing single crystals are, a single crystal can be grown from solution. We were already talking about that. Then from vapor and from melt. So solution is the most normal thing which comes to our mind, and it is the simplest case. So we have an aqueous solution. So water is soluble at low temperature, reactions are there. So generally solution growth is at room temperature or low temperature, or maximum we go to around maybe 50-60 degree or something. But when we are going to go at high temperature, or we can apply pressure to like dissolve material. So it is called the hydrothermal. So we will be coming to that. Hydrothermal growth is used for the growth of quartz crystal. And a more general form of solution growth is called the flux growth. So like we add a flux. So how it is done is there. So like you can use a similar material or some different material, which will be, actually it is a solid, but it goes to at high temperature and it dissolves the material, and then we can grow. So it becomes a solution only, but not like a solvent. We are not using like water or ethanol or some organic as a solvent. We are using a solid material as a solvent. So it is called the flux growth. So advantages of solution growth is like it is usually the slowest process and applicable only to material which are reversibly soluble. So you can get it solved. It dissolves and then it can precipitate out. And quartz can be produced by hydrothermally. This is like what is done in commercially also. And the biggest advantage of solution growth is it is inexpensive. So you require very few things to do and cost intensive. So it is it is basically precipitation from a supersaturated solution, and saturation can be achieved by slow cooling the solution or evaporating the solvent and or adding things to solvent to reduce solubility. Like you said, you can add a foreign particle which will reduce the solvent solubility of the solvent. So what should be the solvent? So what should be the property of the solvent for the solution growth? So it should have high solute solubility. It should have positive temperature coefficient of solute solubility. What do you mean by this? It means that at a given temperature T1, which is greater than T2, the amount of material which we can dissolve in the solvent. Let us say we can dissolve X amount at T1 temperature and X2 amount at T2 temperature. So it should be greater. Means as high temperature, high positive temperature coefficient of solute solubility. So at high temperature, the amount I can put more material into it. And so as I decrease the temperature, when I go to T2, so they will start precipitating out. Second thing is that low volatility, because it should not degrade, or it should not have small vapor pressure. Okay, it should not start evaporating, or if I am heating it, it should not become volatile. It should be low viscosity, less corrosion, and non-toxicity. And solubility of the solute is dissolving the solute at a constant temperature. And solubility of the material decides the amount of the material available for the crystal growth. So we have got three, that is the slow cooling method and slow evaporation method and the temperature gradient method. So what is the slow cooling method is nothing but we have, like I said, we have a bath and we dissolve some X1 amount at T1 temperature and slowly we bring it to T2 temperature. So that this is at supersaturated at X1. So we will have some material growth in this. Okay. Or if you want to have a nucleation and all, so we can put a seed crystal. So generally, and the crystal growth starts on this seed crystal. Okay. So this is cooling method. We are decreasing the temperature. Or very similar to this, we can have a temperature gradient method. So that here we are maintaining at T2 temperature and here we are maintaining at T1 temperature. So what is happening? In the same system, we are maintaining two temperature. So that at the top I am maintaining at a lower temperature and below I am maintaining at using some heater coils or something. Okay. And my seed is here. Initially I am putting, so here because more amount will be dissolved and then I am stirring it. So some material will go here. It will, because this is here the temperature is less, it will start to get condensate and it will start. So the crystal growth is happening. So this is the temperature gradient method. Or we have like slow cooling method is that rather than slow cooling, we can start the material, your solution can evaporate. So your crystal is growing here and you are maintaining it at a temperature like say T1 and it is evaporating. So supersaturation is, you are attaining supersaturation and precipitation is happening. So these are the general methods of solution growth. Now coming to the hydrothermal technique. So this is also a solution growth, but this is where here till now I was talking about like temperature T1 or something, which is always less than the boiling point. Now, if we are using a solute, a solvent above the normal boiling point, so how we can do that? And in this water medium and high temperature we are using, and high pressure is also used, so that we can achieve and go to a temperature which is high above the boiling point. And water functions as a solubilizing phase. Pressure is agent. Often mineralizing agent are added to enhance the dissolution, transport of the reactants, and crystal growth speeds up chemical reaction between the solids. So it is a useful technique for the synthesis and crystal growth of phases that are unstable in a high temperature preparation in the absence of water. So we have a temperature gradient between the opposite ends of the growth chamber. The solute is dissolved at the hot end, while at the cooler end, it is deposited on a seed crystal. Very similar to what we have seen earlier also, like temperature gradient part, but here we are also applying pressure. So advantages is that it has the crystalline phases. Which are not stable at the melting point. So we can make some at the melting point, some of the crystalline phases are there, which is not stable, or there is a phase transformation, and useful for material with very high vapor pressure. So because it is grown under pressure, or suitable for large size. But the disadvantages is it is a you require the autoclave. So what is autoclave? So this is autoclave. Autoclave is nothing but a pressure cooker. So you have a solution which is inside it. You put the solvent, the solute and the solvent is there, and you seal it, and then you are taking it to a temperature above the boiling point. But because it is under high pressure, so there will be, and the vapors are there, it will take the material and the crystal will start happening. So this is an autoclave, single crystal which the new growth forms. So this is the seed crystal, and the cooled mixture will fall down and heated mixture will go up. And it is a enriched solution of silicon oxide. So basically it is used, this is typically used, as I said, for the growth of quartz or the single SiO2. So why importance of quartz? Just I will briefly tell why quartz is important. Like in the last lecture, we heard about the importance of silicon and all. But why quartz is important? So because it is a non-centrosymmetric crystal, so it generates a voltage in response to applied mechanical stress. So your watch all have the quartz crystal. And compressive strength around 100 disturbs crystal symmetry and distorting threefold axis, creating charge asymmetry and electrical charge across opposite crystal faces that generates a voltage. So this is a piezoelectric. So it has got very high demand but very difficult to grow. And as it has a phase transformation from the melting point to the room temperature. So we have to find a solvent. So how the quartz crystal is grown? So what we do, it is dissolved in water using a mineralizer. Solubility of quartz in water is important for the solution growth. But if we see, this solubility is around 0.3 weight%, even at supercritical temperature like 374 degrees, which is very low. It is very difficult. You have to take the water to 374 degrees centigrade. Then also its solubility is very less. So we are adding some agent. So this is called the mineralizer. It's a complexing agent for increasing the solubility. So generally NaOH or Na2CO3. So these are two general mineralizer which are used for the growth of silicon oxide, SiO2 or quartz. So if you see that NaOH, so here it dissolves, it is making it easier for SiO2 to dissolve in water, and then it dissolves in water and then it gets crystallized. So, and in both Na2CO3 and NaOH both helps, but we see that NaOH creates growth rate around 2x times more. So here, like, here it dissolves with only 2OH, where it is 6OH. So then Na2CO3, because of the different concentration of hydroxide mineralizer. And for the hydrothermal growth of silicon oxide, this enriched solution of SiO2 is dissolved at a high temperature and high pressure. So this is the charge. Okay. Heated mixture rises up to the top. So this is very high. We go up to around 400 degrees centigrade. This is tightened. Everything is now like a pressure cooker. There is a gasket is there, washer is there, and these are the seed crystals. Multiple seed crystals are there, and this evaporates the dissolved material. It goes up, then some, and this seed crystal some get, and the rest of the mixture comes back, and this keeps on happening. So the heater sets up temperature gradient. So here the temperature is high, here it is low, so that the nucleation and the growth helps. So natural convection by heat and gravity, the material goes up. So cooled mixture falls back to the bottom and the cycle is repeated. So that is how the crystal is grown for this is the hydrothermal growth technique, and specifically used for silicon oxide in the industry level. And till now it is being used. So can you tell me where SiO2 is used? Like I said, one is watch, right? So in our watch, generally we use the quartz crystal. Anywhere else, anyone can tell me? Any answer?
The quartz tube, at least I've seen them being used in the lab to contain pellets for experiments.
Yeah. So, okay. So quartz tube is there. So there is quartz tube and there is glass tube. So you know what is the difference between them?
The melting points are different, I guess.
Yeah. So how much difference? Any idea? Your answer is absolutely right. So, okay, I will answer that. When we are talking about glasses, so borosilicate glasses and all, so they melt around 400 or 500 degree, whereas quartz melting is very high. So you can go easily up to 1000 or 1100 degrees centigrade when you use a quartz tube. So in any reaction which we are using in the lab, so you can use a quartz tube when you are going to very high temperature. But normal your lab beakers and all, they are borosilicate. Though looking at them, you may feel both are same, but basically their changes is in the melting temperature, and borosilicate they are glass, whereas quartz is a single crystal. Okay. Now we come to the flux growth. So this is also, as I told earlier also, flux growth is also solution growth, but here the material, the flux is not a liquid or it is not a solvent. It is a material, it is a solid material which can be used to dissolve the crystal which we are trying to grow. So we heat the flux to a liquid state, and then we are putting the material for which we are trying to grow, and then we cool it very slowly. So we have got some crystal is there. So like I can tell you some examples are there. So flux growth we can generally flux we can use like SN is there, or T is there, or sometimes PbO, lead oxide. These are used as a flux material. So like I am trying to grow say a tin telluride, SNT. Just an example I am giving. So you can use tin as a flux, or there is some material is there which has got very high melting point, and say any oxide is there which it's going to very high melting point is there, and you want to grow it by solution method. So you find out a material which can dissolve at a lower, you can decrease the melting point of your material to a low, dissolve it in a flux and then cool it slowly. And by cooling it slowly, the crystalline forms will be there, and then it precipitates out from the flux, and then you can take out. So it can be used for alloys or intermetallics and all those things. And the main disadvantage of flux growth is that some incorporation or impurity will come. So whatever flux you are using, so the incorporative, that will get incorporated, like it will be as an impurity in your growth. So it is good for alloys and intermetallics. Low strain is there because you are slowly cooling, but good choice of flux lowers the required temperature and you don't require any special material or equipment. You just put your flux, and your just like example is there, like we can intermetallics are there, like Mn, manganese, copper, I think Sn, some kind of intermetallics are there, and Sn can be used as a flux. So the melting point of tin is very low, and or Fe is there you can have. So all very high melting point material, but it can all dissolve. But here the ratio of the material which you are growing, the crystal, and the flux, this is the flux, is very important. So flux is taken in a very large amount. So like 20:1. So this is the flux by weight, and this is the crystal you are trying to grow. So this is by weight. Huh? So 20 times by weight flux you are putting, and then just 20:1, that kind of ratio of flux is being taken, and then you are dissolving it. The material dissolves in the flux, and then crystals are grown. But generally in this method, very small crystals are grown, and generally used for like research purpose, when you want to do some magnetic measurements or some new materials you are studying. So there you can use this flux growth method. And need for extended temperature control, because you have to cool it very slowly. Usually we get very small crystal. This is a disadvantage. And we have to find a suitable flux and suitable crucible. And it is very difficult to remove the flux, because when you come to room temperature, because your flux was a solid material, so you have to either like pour it at high temperature so that the flux is removed, or you have to dissolve the flux. Like NaCl or KCl, these materials are also sometimes used as a flux for the growth of some halide or fluoride materials. So this is it is a solution growth, but here both the material, the solute and the solvent are solid at room temperature, but at high temperature they can be used as a solute and a solvent. Now we come to the single crystal growth from vapor. So this is mainly we are subliming. So you have this is there. We have some material. We have a heater. It has got two temperatures, and you sublime it, and then it gets carried with using some vapor transport, and then it is settled here. So we can have chemical vapor transport, or pulse laser deposition is also one kind, or metal organic chemical vapor deposition. So you are not dissolving it, it is coming sublime, or it is in the volatile state. So we will be using and studying this more in the our thin film part, but it is useful for the growth of epitaxial thin films, and it requires either high vapor pressure. The material should have high vapor pressure because we are trying to evaporate it, or ability to evaporate it, it should be there. Then it requires a substrate or a seed on which we will be growing the crystal. This is a very slow process, and the vapor can react with the container, or we require specialized equipments. Okay. Now we are coming to the main part of the growth from melt, which is the most widely used. So we will take just 1 minute break, and then we will start for this part. Okay. So you can just think about whatever we have done till now. If any question is there, we will try to solve here, or we will just finish the growth from melt, and then we will take up questions. Okay, so just 1 minute break. Okay, so now we have got only 10 minutes left. So I will just go through few things on the melt growth, and then we will have a question answers or something. So my question for today is like, which are the two energies which compete with each other during the nucleation process? Which are the two energies of the system which compete with each other during the nucleation of the single crystal, the nucleation at the nucleation. Okay. So everyone understood the question?
Yes, ma'am.
Okay. Huh? So this is the only one question for today, and very I think we you know already because we have discussed it. Just put it on the mail and you can mail it to me. My email ID I have already shared, so that we can do. Repeat. Okay, you want to. So what are the two energies which compete with each other? The two energies of the system which compete with each other during the nucleation process. And one energy leads to the growth and one energy leads to the destruction. There are two energies out there.
Ma'am,
So
we have to
I
give
have told
answer.
everything, just you have to name them. Okay?
Yeah, we have to give answer now or mail?
No. You have to mail it to me. No
Okay.
answers. Okay, that
Okay.
is your assignment for today.
Okay.
Okay? So now we will be coming to the most important, that is the growth from melt. So why it is important? That because when we were talking about silicon, yesterday we were talking about silicon, our last lectures, main semiconductor industry, all your ICs and everything. So silicon is grown from melt. So if you see the world crystal growth, so around 60% of the crystals are grown through the melt and mainly dominated by silicon. And then gallium arsenide, all those things. Okay, I will repeat the question in the last. Just wait. So that's why growth from melt is very important. So there are variety of techniques are there from melt growth, and they are the names are, you may think they are a bit difficult, but you will come to know about them. So Verneuil principle is there, technique. Then Zekrowski, which is the most important. Our gallium arsenide, silicon, germanium, these are all grown by the Zekrowski technique. Then Chiropoulos is there. So Chiropoulos we are using for the growth of sapphire. Not very high quality, but your very high your mobile glasses, which we generally call gorilla glasses and all. So they are grown by this Chiropoulos technique. And then we have got the Bridgman. So most of the halide crystals are there, like sodium iodide, cesium iodide, which are used for radiation detector purpose. They are all grown by the Bridgman technique. When we have got some other techniques like the laser heated pedestal growth, micro cooling, floating zone, and so on and so forth. So these are the main, but I will not be covering all of them in our class. So today I will not be completing this. We will be just completing some initial of melt growth. And then tomorrow onwards, we will start with the Zekrowski, Chiropoulos and Bridgman and something of float zone. But starting with the Verneuil, first is like advantages of melt growth. So melt growth usually has the highest volume growth rate. So like using the melt growth technique, like I'm talking about silicon crystal growth. So you can imagine a silicon crystal of 12-inch diameter. 12 inch is like 1 feet. So that much diameter single crystals of silicon can be grown and with a length of 3 meters, 3 meter high and 12 inches diameter. Single crystal of silicon are grown in the industry today using the melt growth technique of Zekrowski. So this has got the highest volume growth rate. It is applicable to material that melts congruently and have no destructive phase changes. That melts congruently means if we have got a material AB is there and we want to grow. So it has got one element A and another element B and we want to grow it using the melt growth technique. That means if we are melting AB, so at the given temperature, at the melting point, in the liquid form state and in the solid state, AB should be, this phase should be stable. So in the, say at melting temperature Tn, AB is there. So in the liquid phase and the solid phase, this phase should be same. So that means it is congruently melting and it is not dissolving. So say like AB, you can think, okay, why it should be different phase? But say AB2, we are growing a material. And it can happen that at any given temperature Tx, it may be in the solid phase, it may be AB, whereas in the liquid phase, it can be AB2. This phase is at temperature Tx. In the liquid, it is AB2, whereas in the solid, it is AB. It can happen like that. And this kind of material, we cannot grow by the melt technique, because this is called, they are incongruently melting. So only material which are congruently melting, we can use them for the growth of melt. And if they are incongruently melting, then we have to use different techniques to make them congruently melting. Then they are grown at very high temperature. So there is always this is a disadvantage, that there can be some contamination and we will require some crucibles to hold them. And using the Zekrolsky and the floating zone method, we can grow crystals, dislocation free crystals can be grown. Because in this techniques, you will come to know tomorrow that we can play with many parameters, which are affecting the nucleation and the growth. The floating zone method can yield large crystals of material whose melt have a very high ratio of surface tension to density. This point I will come and explain when we will be coming to the technique. And Bridgman method has achieved a noteworthy renaissance for the relatively clean production of high quality crystal with excellent diameter effects. Okay, now coming to the first technique, which is the Verneuil's prism. So this is the genesis of all crystal melt growth techniques. And this was the first furnace used by Auguste Verneuil. He is a French person. And he used this technique for the growth of ruby crystal. So this was developed in 1902. And this is like the genesis of all melt growth crystal growth techniques. And you will see that all melt growth crystal growth techniques are a combination of Verneuil method. And they are used to grow, this method has been used to grow ruby crystals. So this is a ruby crystal. Ruby is nothing but Al2O3 with chromium doping. So this is Al2O3 crystal. So this is the crystal which is grown. So in this method, what he is doing, this Al2O3 is there. Al2O3 is melts at very high temperature. So temperature is more than 2000 degrees centigrade. So the starting material, that is alumina, Al2O3, is finely powdered and placed in a container. So this is kept here. And this is the furnace. This is the furnace part. So from one end, he is putting hydrogen, and from one end, he is putting oxygen. And a flame is produced here. And because Al2O3 with chromium is there, it is coming and flowing down. And the amount of material which is flowing down can be controlled from this orifices there. Yeah. So from here we are controlling the amount of material, like the growth rate. Okay. And because this hydrogen flame is there here, so it will form a droplet, and there is a seed crystal here. If you see here, so there is a seed crystal at this point. So that is the nucleation. And then the growth rate is increased and we get a ruby crystal. So oxygen is supplied into the furnace, which carries the powder particle down a narrow tube. Combustion occurs at the point where the narrow tube opens into a larger one here, and the flame at least 2000 degrees centigrade hot at its core melt the powder into small droplets which fall onto the earthen support rod placed under beneath. This is the seed crystal eventually forms as more droplets fall into the seed tip. A single crystal called bowl or ingot starts to form. So this is how the first melt growth technique of crystal was formed, and this is the one oil method. So this is still now used, this though it is very crude, but this technique is still used for the growth of very small size ruby crystals. But very big crystal, it is very difficult to grow using this. So this is primarily used to produce ruby and sapphire varieties as well as diamond simulants, rutile and strontium titanate. The method is still the least expensive way to make sapphire and ruby. In principle, the process involves melting the powdered substance using an oxygen-hydrogen flame. The melt droplets crystallize to a single crystal seed, which grows to produce the crystal ingot. The process is considered to be founding step of modern industrial crystal growth technology. And the technique remains still wide used today. And this is artificial gemstone, it is still used. So like ruby is an artificial gemstone, it is still used. So this is the starting of the melt growth. So I will stop here, and then from tomorrow onwards, we will go more with the different melt growth techniques. Okay. So if you have got any questions, so just 5 more minutes I can take, and then we will stop. Maybe 2-3 minutes because we are already running late. So any question, just let me know. Okay. Okay then. So you remember my question is there, and you give me send it on my mail, and then on Monday we will start with the single crystal growth, and we will carry forward with the thin film part. Okay. So
Okay.
thank you.
Thank you.
Have a
Thank you.
good day.
Thank you, ma'am.
The next class is on Monday, yes. And the question I will just repeat again, that what are the two energies which compete with each other during the nucleation? Okay, during the nucleation part of the single crystal growth. So that was my question. Okay. And Monday we will meet again at 2:30 hours. PM. Okay. Bye. Have a nice weekend. Bye.